Okay, great. Lutfi Al-Sharif is going to give us a paper on using machine learning to estimate the traffic mix and intensity in a building. Okay, I'll actually save you some time, and your biography we can read in the details. Again, if you agree, I think we'll go to more questions. But again, he's published over 50 papers in peer-reviewed journals in the conferences, and he's co-inventor of 4 patents and co-author of the second edition of the Elevated Traffic Handbook. Thank you, Lutfi.
Thanks, Phil. There's a minute gone from the presentations. That's okay. I'm just going to start with a quick note. I mean, last time I presented, Adam was in the room, and at the end I said this is the simplest way to present it. I can't present it in any simpler way. You remember Adam? And I thought I didn't really understand what Adam meant at the time. And then afterwards I thought, I think what Adam means is if this is the simplest it can be presented, what on earth would it have been like if it was actually presented in a complicated way? And I think that's, is that right? You don't have to answer, that's it. Okay, I'm the only thing that's standing between you and the drinks bar, so I'll try to be as fast as possible. Okay, so those of you who remember, 2 years ago, Richard had the idea of placing an accelerometer. Someone talked about an accelerometer being placed on the doors this morning, but that was for identifying the door movements. This actually has a different objective, is placing an accelerometer in the car, which is fascinating, in order to be able, obviously, to understand the movements of the car, which is straightforward, but then start estimating other parameters in the car related to traffic, not to the doors. So, and this is actually quite a usual problem. You have a complicated system. You can't see some parameters inside the system, but you can measure others. And by measuring others, you can estimate those parameters which you're interested in. This is basically as simple as possible, Adam. So, we place an accelerometer with ample storage inside any lift car, record the acceleration. From the recorded acceleration, we derive the velocity and the position, and then we derive the up stops and the down stops. From the stops, we deduce the mode of traffic in the building. Is it incoming? Is it outgoing? Is it interflow? And I'm going to exclude completely the inter-entrance because I think it's irrational, so we'll leave that. So people moving between entrances doesn't make sense to me. And this is an example. So measuring the acceleration, that's the acceleration signal. We're only interested in the Z direction. And then from that, we deduce the speed, and then we deduce the position. These are examples of seismic accelerometers, which have a small mass moving inside on a spring with some damping. But the more interesting ones are the modern, the nano or the MEMS, micro electromechanical system accelerators. They have 3 axes, X, Y, Z. We're only interested in the Z direction. You can have it as an application as well. Most of our mobiles will have an application, and if you download it from Google Play, you can actually play around with it for hours. You can put it in the lift car. You can download the data, and get it to Excel, and process it. So we've taken a hypothetical building. So this building has, we're assuming 13 passengers in every round trip, 10 floors, 2 entrance floors and 8 occupant floors. The entrances have a bias of 30% from the car park, 70% from the ground floor. And obviously with great processing power these days, we can do a trial of million trials. So run a million trials, get the data about that building, hypothetical building, and then average the data. This is a typical position in the building and time. And this is a spatial movement diagram. Obviously, this is up peak only, as you can see. So it's stopping in the up. It's not stopping in the down. But we'll keep on going through that route continuously. The expression of entrance floor and occupant floors. So the definition of an entrance floor is a floor by which passengers enter or exit the building. They can't live on that building, on that floor. Occupant floors are floors on which passengers can occupy, and move. And that's an important definition. It's an important distinction. So we take this building, we run it for 1 million times for different types of traffic, and then we can have a look at the results. So I've used the word intuition. Probably the word intuition is not the correct word. If you can come up with a better answer or a better definition, then I'll be very interested to hear it. I don't think intuition is not the correct word, but let's have a look. So what we're measuring is up stops on entrance floors in a round trip, and up stops on an occupant floor in a round trip. And this building has a signature. So this is a signature which you will get from this building under these conditions. I've hidden the conditions, and you're going to guess them. This is the first question. So during this round trip, this lift is making nearly 2 stops at the entrance floors on the way up, and nearly 6.6 stops on the occupant floors. It's making no stops in the down, and it's making no stops in the down. What is the mix of traffic? Up peak. That's very intuitive, isn't it? Is intuitive the right word? So that's 100% up peak. That's obvious. It's an extreme case. Another extreme case. We have a building, 0 up stops on both floors, 2 stops, down stops on the entrance floors for people to leave, and 6.59. It's obvious, this one, down peak. Now it gets a bit more tricky now. No stops on the entrance floor in the up, no stops on the entrance floor in the down. All the stops are on the occupant floors, interfloor, that's obvious. So these are the 3 easy cases. It's usually very good to start with easy cases because you can start understanding the situation. Now it gets more interesting. What about this one? Any conclusions we can come up with?
Canteen in the building? Maybe a canteen in the building?
It's a good start. It's a good start, but I want more specific answer. 50-50. So there's 50-50 there. That's obvious there. So it's 50 up, 50 down. It's identical. We don't know if there's any interflow or not. There is. So there is actually interflow. Can you see now it's getting more complicated? Intuition doesn't work anymore. Any suggestions? What can we do now? We're not getting those nice, easy cases in there. There must be a better solution, a better way. This is, in fact, an ideal case for machine learning at this stage, from this stage onwards. So this, now you can see clearly this ratio to this ratio is not the same. What does it tell us? It tells us something intuitively as well. Down is stronger than up. Is it in the ratio of 1.6 to 1.2? No. It's not as easy as that. But there is a relationship. So this is 15-30. So down peak is stronger, twice as strong as up peak. But 1.66 is not twice of 1.2. And the point from all of these 5 questions, we now need machine learning. And this is a suggestion of this research project, is to generate so much data, big data, train the algorithm on them, and then it can actually give me this answer from these answers. If you understood that, you've understood the project. Who understood that? Okay, let's look at some results. This is a type of machine learning. We all use regression. Regression is one of the simplest forms of machine learning. What we do, we try to actually find the relationship between one variable and another variable. Now, obviously, true machine learning would be much more complicated than that. So to conclude, so the aim of this research is to place an accelerometer inside the car. 2 years ago, it was actually trying to find the number of passengers. Today, it's actually trying to find the mix of traffic. we get the number of stops in the up direction, number of stops in the down direction. We then apply a machine learning algorithm to the data, calculate the mix of traffic prevailing in the building. So we can find out, this is simply by just placing an accelerometer in the car. We've only used regression, conventional regression techniques for this, but obviously the full aim is actually to use more sophisticated machine learning algorithms. I'll finish with this. Who's watched the Oppenheimer? Yeah? Well, you will remember it was in New Mexico, Los Alamos. What is relevant to us today is that Monte Carlo simulation started from there with von Neumann and others, although von Neumann was not actually mentioned in the film for some reason. I don't know why. But that is, and thank you much for your attention.
Thanks, Lutfi. Any questions to the floor? Rory.
So you're using MEMS accelerometers.
Yes.
Have you considered the accelerometer drifts that you have with a MEMS accelerometer, and also integration? Over time, your integration errors accumulate.
Yes, yes. I mean, he's the expert in getting drift out and integrating and so on. But yes, there are very, very well established techniques. For example, once you integrate speed, you will find there's actually, you know that speed is 0 and should be 0 here.
Right.
So what you basically do, you do a correction. And it's easy in lifts because you know when the lift is stationary.
Yeah.
So you could do that,
So
yes.
yes. In your model, you've been doing that, or?
Yeah, I haven't.
Okay.
I've just showed the accelerometer to show the context of the
concept
project.
of what
yes,
you're doing.
the context of the project. That's how you start with. Yes.
You started with just a simple regression rather than
yes,
neural network or CART or something like that.
Exactly.
Okay.
What we'd like to have is to have the full machine learning algorithm. But all we've done at this stage is just linear, not even linear. It's just basic regression.
Okay.
Yes.
Thank you.
Okay.
Interesting.
Richard.
I was just trying to remember when you started work on this problem. Was it the 1980s or was it the 1990s?
Yes, 1992.
I just wondered when you think you might actually solve
when
it.
ISP started. It's interesting, 1992, you would never have been able to get away with 1 million iterations in 10 seconds. So the processing power has moved so much now that this has actually become available. Then it was equations. You had to derive equations, which is obviously becomes very tiresome and lengthy. The processing power we have now is absolutely amazing. So you can generate 1 million scenarios for a building in 10 seconds. And you get the data about that building and you start using it. So what is hungry for big data? Machine learning. So machine learning is absolutely hungry for big data. We're not talking hundreds, we're not talking thousands, we're talking millions of pieces of information. So as Richard said, it started in 1992 with equations and analytical equations. Hopefully, at some point in time, we will actually put an accelerometer inside the car, leave it, and then you would come up with every passenger who went in, went out, and the mix of traffic in the building. A very nice case of estimation.